All right, let's just dive right in. We're going to talk about a threat that's quietly looming over every single password, every bank transaction, every secret we've ever trusted to the internet. It's a fascinating story about a new kind of superpower and the frantic race to build defenses against it.
And it all starts with a really strange question. Right now, as we speak, governments and hackers all over the world are stealing and hoarding enormous, unbelievable amounts of encrypted data. The thing is, they can't read any of it. It's all just gibberish to them. So why on earth are they bothering?
Well, the answer has this kind of chilling name: store now, decrypt later. They're playing the long game. The bet is that the secrets they're stealing today, things like national security files, your financial data, corporate research, will still be incredibly valuable 10, maybe 20 years from now. And they're convinced that by then, they'll finally have the key to unlock everything. And look, this is not some sci-fi movie plot. This is coming straight from the National Security Administration, the NSA. They've put it in black and white. A powerful enough quantum computer will shatter the very foundation of our digital security. So, the key thing to get here is that the data is being stolen now. The threat is already here, even if the superweapon to break it isn't fully built yet. So to really understand the threat, we first have to appreciate the digital fortresses we all live inside every single day. I mean, the encryption we use has been our silent guardian for over 40 years, and it's been incredibly good at its job. But how does it actually work? You know, for the longest time, sending a secret message was a real hassle. You literally had to meet up in person to share a secret key. But then, in 1977, three brilliant scientists, Rivest, Shamir, and Adelman, had an idea that changed absolutely everything. They created a system we now call RSA. The genius of RSA is that it works on a two-key system. It's really clever. You personally pick two massive secret prime numbers. Then you multiply them together to get an even more massive public number. Now, anyone can use your public number to lock a message and send it to you. But, and this is the magic part, the only person who can unlock it is you, because only you know those original two secret prime numbers. So just how strong is this system? I mean, really? Well, let's put it this way. If you took one of the fastest supercomputers on the planet today and told it to figure out those two secret primes just from the public number, it would take that computer about 16 million years. So yeah, that's a pretty secure lock. Or at least it has been. Because now, everything gets turned on its head. Enter the quantum computer. This isn't just a faster version of your laptop. It's a machine that operates on the bizarre rules of quantum mechanics. It's a completely different way of thinking about computation. And the fundamental difference really boils down to this: a bit versus a qubit. A classical computer bit is simple. It's like a light switch. It's either on or it's off, a 1 or a 0. But a qubit? Thanks to a wild quantum property called superposition, a qubit can be a 0, a 1, or some combination of both, all at the exact same time. And this one little trick leads to a ridiculous exponential explosion in power. With 2 qubits, you can do 4 calculations at once. Okay, neat. With just 20 qubits, you're doing over 1,000,000 calculations at once. By the time you get to 300 qubits, you can represent more possible states than there are atoms in the known universe. It's just mind-bending stuff. But, and this is a huge but, there's a massive catch. You can't just peek at those million-plus answers. The moment you try to measure a qubit, that beautiful superposition just collapses, poof, and you're left with just one single random answer. All that other incredible information just vanishes. This actually makes quantum computers totally useless for most everyday tasks. Useless. That is, unless the problem you're trying to solve is structured in a very specific way. And as it turns out, breaking RSA encryption is one of those special problems. The solution is an incredibly clever piece of math called Shor's algorithm, which isn't about brute force. It's about hunting for a hidden pattern. So what does this pattern look like? Shor's algorithm exploits this neat little quirk in modular arithmetic. If you do a specific calculation over and over again, the remainders start to repeat in a predictable cycle. See it here? In this simple example, the pattern of the remainders repeats every 10 steps. Finding the length of that cycle, what's called its period, is the secret key to breaking the entire code.
So, how does a quantum computer find that all-important number, the length of the pattern? It uses a mathematical superpower called the quantum Fourier transform. It's designed to look at that entire messy superposition of all the possible remainders at once, and from that chaos, it pulls out one single beautiful piece of information, the frequency of that repeating pattern. And with that number, it's game over for RSA. So that's the bad news. Our supposedly unpickable lock has a very specific, very powerful key. But here's the good news. The smartest people in cryptography have seen this coming for a long time, and they've been in a race to build entirely new kinds of locks.
And this has been a massive, coordinated effort. Back in 2016, the U.S. National Institute of Standards and Technology, or NIST, basically threw down a challenge to the entire world. They held a competition to find the next generation of encryption. They got 82 different proposals from cryptographers everywhere. And after years of intense, rigorous testing, they finally announced the winners in 2022, our new quantum-resistant standards.
One of the leading candidates in this new family of defenses is based on a completely different kind of hard problem. It's called lattice-based cryptography, and it's all about the mind-bending difficulty of navigating through a super complex, high-dimensional grid. Okay, here's the core idea, and it's actually really cool. You can describe a grid, or a lattice, with a set of really nice, simple, easy-to-use directions. Let's call those the good vectors. But you can describe the exact same lattice with a set of really messy, skewed, complicated directions, the bad vectors. If you only have the bad vectors, trying to find the shortest path between any 2 points is an absolute nightmare. And that's the secret. The good, easy-to-use vectors, that's your private key. The messy, scrambled, bad vectors, that's your public key. Now, just imagine this problem not in 2 or 3 dimensions, but in over 1,000. If you have the secret key, finding your way around is a piece of cake. But for an attacker, even one with a powerful quantum computer, it's pretty much impossible. So what does all this mean for us? Well, it means that right now, our entire digital world is in the middle of a massive, mostly invisible security upgrade. And it's happening thanks to some incredibly dedicated, brilliant people working behind the scenes. It's really easy to just focus on the threat, on the scary part of the story, but it's so important to remember that there's this global army of unsung heroes, researchers, mathematicians, cryptographers, who are working tirelessly to build these new defenses and make sure our secrets stay safe. And this isn't just some plan for the distant future. The transition is already happening. Governments and major companies are starting to roll out this new post-quantum cryptography to protect literally everything, from critical infrastructure and military secrets right down to your personal messages and bank account details. You know, this race between the code makers and the code breakers, it's a story as old as secrets themselves. Right now, we're building incredible new digital fortresses, ones designed to withstand a full-on quantum siege. Which, of course, leaves us with one final crucial question. What's going to be the next weapon that nobody even sees coming?